Pre-orogenic history of the Tunisian block. The studied area, as illustrated in Figure 4, shows that this TB became individualized very early in Mesozoic times along with its determined limits. Tunisian basin and continuously mobile boundaries. Whereas the Saharan Atlas in Algeria is composed of a folded and faulted chain elongated in the SWN direction, it forms an almost isosceles triangle in Tunisia. This latter terrain corresponds to a true continental block, whose origin is precisely linked to its paleogeographic history, which is dominated by its three boundaries, undergoing continuous tectonic remobilization, controlling the geometry, morphology and filling of the basin, Fig. 4. More precisely, these boundaries correspond to mobile zones from the early Mesozoic onwards, with the formation of sedimentary wedges, gaps and unconformities, Biely, 1956, 1991 and Biely et al., 2000, Rouvier, 1977, Layam, 1999, Jauzein, 1967, Sawyer and Tricart, 1987. In this way, the Tunisian Atlas appears to inherit its present morphology from the early and continual compartmentalization of the basin, which is tectonically inverted from Tortonian times onward to form the folded Atlas chain. The three boundaries of the block form mobile zones of variable width associated at depth with vertical faults of the pre-Triassic basement, Midasi, 1982, Morelli and Nicoli, 1990, European Geotraverse, 1992, Piquet et al., 2002, Gatney et al., 2005. The southern boundary, which, moreover, is prolonged in the extreme southeast of Tunisia, corresponds to a coastal depositional environment, sometimes of evaporitic type but in a subsidence zone, Kalmoun et al., 1999, Susi, 2002, with a series of depocenters and tectonic highs succeeding each other from NW to SE, the Shots Basin, the Tobago High, the Tatouine Basin and the Nafusa Highs in Libya, Asawi, 1984, Bouaziz, I995. All these morphostructural features result from transtensive movements of the GNTC in an overall NS extensional regime, in echelon EW normal faults. At this epoch, sedimentation was occurring in a typical intracratonic basin. The northern boundary corresponds to the faulted edge of the deep trough, Biely, 1956, i.e. an open marine basin. This basin contains pelagic deposits displaying a margin-type character with SWN trending active faults, L. alia Teboursouk, Boujaberlerbius Gafour, for the principal ones. These faults are probably inherited from the basement, and are picked out by diapirs. They could be integrated into a transform margin on a much larger scale associated with a sinistral strike-slip fault zone in relation to the Assuresh-Gibraltar-Sicily system, Dercourt et al., 1985, Dewey et al., 1989. The eastern boundary is generally expressed as a NS trending axis of dome-type diapiric highs with condensed series, gaps, wedges and discordances, Germelin et al., 1989, intersected by local depocenters associated with grabens or hemigraben structures linked to the regional extension and arranged according to transverse faults following the axial trend. Finally, in the Jurassic, in spite of the scarcity of outcrops and subsurface data, a synthesis of sedimentological and paleogeographic studies, Kalmoun et al., 1999, Susi, 2002, combined with the existing tectonics allows us to propose a simple geometrical model of the Tunisian basin at that time. Three unstable zones are arranged around a resistant central block with little or no subsidence, and are subject to the remobilization of pre-Triassic basement fractures. As a result, this basin displays clearly intracontinental characteristics. Subsequently, these three unstable zones exert a more or less important influence on the geometry and development of the basin at different times. A positive zone appears corresponding to the Kairouan Island, Mourabit, 1981, clearly delimited in the east by the CNS and the GNTC in the south undergoing more subsidence. The tectonic regime is thus extensional with a maximum lengthening towards the knee, Riggin et al., 2010. At this time, the eastern boundary becomes increasingly positive, while, throughout the region, we observe the development of condensed series, gaps and wedges of aptionage called the Gafsa group by Imre Bay, 1981. Sometimes, the entire Gafsa group is even reduced to a meter-thick quartz-bearing dolomitic level named the Boozer dolomite by Germelin, 1984. Among other factors, This mobile and positive zone is the result of diaperic phenomena which probably begins at the end of the Triassic and which ceases, at least temporarily, at the end of the Aptian, since, along the entire length of this boundary, the Cenomanian is discordant on various units ranging from the Triassic to the Aptian. At the end of the Aptian, the tectonic regime is shown to consist of a SWNE extension, Bismuth et al., 1982, Bolton-Hagen, 1985, Sawyer and Tricart, 1987, Fecchi et al., 2005, Riggin et al., 2010, with a strong strike-slip component, transtension, on the megablock boundaries. The Tunisian block temporarily loses its individual character as a consequence of the generalized transgression expressed in Tunisia by the Zebbag formation Sinsulato, Biralet, 1956, Luning et al., 2004. In detail, however, the N, S and D boundaries remain mobile with high zones in the east, a deep basin towards the NW, formation Barlol, and a subsident southern corridor. During the Cenomanian, the tectonic regime is predominantly extensional, Bouaziz et al., 2002. The distribution of depocenters is inverted along the three boundaries of the block. The CNS becomes subsident, with the development of a succession of depocenters and highs, frequently of halokinetic origin. The western extremity of the block shows a tendency towards emergence reflecting the appearance of the Kasserine Island. We may conclude that, since the Jurassic period, the eastern part of Tunisia, mainly to the east of the CNS, remains a subsident zone, with, however, the existence of some more marked basins, Allows, 1984. Throughout this era, some major changes occur in the basin geometry. The Kasserine Island is superposed on the southernmost part of the Tunisian block. Indeed, Isopch and Facies maps, Bishop, 1975, Riggin, 1991, Riggin et al., 1994, Sayer et al., 1998, Ben Ferjani et al., 2006, clearly show the presence of shallow basins, in the NW and the SW, nummulitic and phosphatic facies, which become deeper in the east, troughs of the Gulfs of Tunis and Gabes. During this epoch, a NWSE extensive and or transtensive tectonic regime controls the sedimentation, thickness and facies, in the Frisian Basin, Riggin et al., 1994. The deposits are arranged in isofacial bands almost parallel to the CNGT trend. The Kasserine Island gradually loses its individual character to become connected finally to the Saharan continent. The predominant tectonic regime is also transtensive, but we observe a change in orientation towards a SWNE trend, Gormelin et al., 2000. This radical change in basin cartography is probably linked to the modification of Africa/Europe kinematics at this time, Dewey et al., 1989. Although the area of emerged land tends to migrate northwards, the shoreline is always constrained by the NWSE trend. The tectonic regime is characterized by a SWNE extension, Blondel, 1991, Yaik, 1997. Since the Jurassic to the Oligocene period, a succession of basins and shoals is observed and controlled by continuous mobility of the three faulted corridors, DZ, NSC, GNTC, delimiting the TB associated to diaperic movements. The corridor's mobility attains his paroxysm during three major tectonic crises, at the end of the Aptian, the Frisian and the Oligocene. Each crisis is marked by a momentary stopping, Aptian, Epresian, or definitive, Oligocene, of halocenetic ascension. At that time, Tunisia can be regarded as an intercontinental basin at the northern margin of the African Craton, characterized by depocenters directly related to the activity, reactivation, of pre-existing faults. In this case, mobility is concentrated within an inus-trending tectonic bundle in a transtensive regime. For example, the structural and tectono-sedimentary study of Jebel el Homra to the west of Kasserine, central Tunisia, underlines the predominant role of paleostructures acquired during the evolution of the South Tethyan Basin, and their influence of the present-day geometry of the fold belt. Indeed, the existing pattern of folding and faulting results directly from tectonic blocks formed during the Aptian. Hence, the depocenters appear as two pull-apart basins bounded by a lower-shaped structure, Figure 5. Shown by small arrows. Black arrows, direction of extension, Riggin et al., 2010. Lastly, The existence of tectonic nodes supports the hypothesis that diapirism can induce local tectonic extension. The tilted blocks of Jebel el Hamra can be, consequently, the final result of this transtensive tectonics, locally associated to halocinetic vertical movements of Triassic salt. At a large scale, in the African geodynamic context of this period, Garreau and Morin, 1991, Garreau and Morin, 1992, Garreau et al., 2005, Basile et al., 2005, this late Aptian phase, very exactly dated in the studied area to the end of Clansasian age, is integrated in the rifting phase shown by Garreau and Morin, 1991, and all the intercontinental basins of the northern part of the African Craton, in particular in Libya, Gulf of Sirte,